examples or
Yes, examples.
springs?
Huh?
Spring.
Springs, yes.
Sound.
What else? Huh?
Sound.
Sound. But in probably no one of us will get money for describing sound or write scientific papers and so on. Although there is acoustics science, but it's not the major stream. But like something where we can show our strengths as researchers, or something applicable. What else is?
Electrons. Or in like a plane wave kind of function.
Huh?
In like a wave kind of scenario.
One can create circumstances when electrons will oscillate. Yes, in our everyday life. Lift hands who doesn't have a cell phone. So it is a radio signal transmission. How does radio signal generated and received? How can you use it if you do not know how it works? Throw it away. So there is a coil that creates magnetic field, and it is circuited to a capacitor. And then the electrons go from one part of circuit to another. When it comes to coal, it creates magnetic field and stores energy there. Then magnetic field creates back electric current. And then it comes to capacitor, creates electric field strengths between the plates of capacitor and stores energy there, and then goes back, so it oscillates. And it is a main principle of radio sending and receiving. We'll go through examples again. A person who loves metallic toys. Plasmons, when all electrons collectively oscillate. Okay, so it's another. So what did we do? I'm still working, and I'm trying to merge together your choices, so that, because right now there are 24 subjects and 14 ones. Yes, I think a dozen will come for sure to presentations, and I plan to bring schedule for your final approval on Monday. I'm half done. I just want your approval, because for some of you I have merged together a couple of subjects, for some of you I didn't, and those who got merged subjects made progress. Completely legitimate. So, map. Methods and models. We are coming to harmonic oscillator, which tells that something is oscillating, and we are considering very small deviations from equilibrium position. Okay? And we are believing that the stuff that we are describing are base quantum features. So everything we learned about quantum mechanics was not garbage. We cannot throw it away, but we can apply it to real life, at least to some objects that oscillate. Near equilibrium, Taylor series elongation, and no one was protesting against Hooke's law and rearranging force constant of mass into mass and frequency, right? And then this will be potential energy. So the higher the frequency, the stronger is response to energy to elongation from equilibrium. Makes sense? And then if we plug in this potential energy into Hamiltonian, then we are challenged by necessity to solve some equations, as usual, in this class. So we may want to describe anything well. Of course, we will have challenges from nature or from our colleagues what to describe, but we want to start from simple things and be sure that we can do things. Of course, we will want to predict future, observables, and maybe some realistic systems, which would be infrared spectra here. Another example, liberations of solvent. So if you have very polar solvent around a dipolar molecule, the solvent molecules will arrange there to follow the force lines of electric field. But if you excite, or if something happens to the molecule that its dipole changes, then the solvent molecules will also slightly change their orientation. So it's not oscillations, it's kind of rotation, but restricted rotation. The word is librations, also an example of harmonic oscillator in chemistry. End of little announcement. Going back to the main problem. So we do have Hamiltonian, and we do need, well, whatever we will need later, we may want to start with simplest thing we can. Find eigenstates of this Hamiltonian. Solve time independent Schrödinger equation. I'm not comfortable with pronouncing it because in the native language of this person, so we need to find such functions, and again, see, they are one-dimensional. We can do many useful things staying in one dimension. And this eigenvalue problem should have infinite number of solutions, infinite number of eigenfunctions, infinite number of eigenenergies, right? Before we were so lucky that equations were easy to solve. So what do we do if you have, how we characterize this equation? So see, this comes from potential, from kinetic energy. This term comes from kinetic energy. Well, if you would drop this term, then we will get an equation that would give us plane waves. But we have a term that depends not on the, doesn't have derivative, and doesn't have a constant in front of the function. It has the, it is proportional to the independent argument. So when we, before we were thinking that we know how to solve differential equations, we were just plugging in exponential and finding the power through some algebraic tricks. Do you think this trick will work here? No. So how would you solve this equation if I would be mean and instead of lecturing I would just give you pieces of paper and okay, example, solve equation. I will not do it, promise. But suppose this scenario, how would you try to solve it? What would be the strategy?
Using a ladder operator?
I'm going to invite you to go to this way, but it is very although it will give right answer, the way of thinking for ladder operators is very, like, for physics and chemistry people. It's not mathematical. It will be very quick and efficient bypass. Professional mathematician not aware of physics and chemistry would probably never do it. So it will be really, really quick and short bypass. So you will spend like 3 hours instead of 10. But this is rather challenging equation. And if you would be mathematicians, or if you follow majority of textbooks, they either declare solution and tell like, we don't care how you solve it, just memorize it and use it, which is unfair, I think. I cannot use cell phone if I do not know how it works. And rigorous mathematicians, there is a standard way to solve anything. Represent, would you like to give an idea?
Sorry, what was the question?
How to solve any equation. How to find any unknown function. if you know that it doesn't have singularities, it is well defined with continuous all these nice conditions.
You could expand it into a Fourier series.
Yes, in a series. So represent it as a summation, a linear combination of some known functions with unknown coefficients, plug it in and solve. It will work, always, guaranteed. But it will be so much pain. So basically, solution of this equation, one is looking at it in the form. And then one looks for polynomial. Like 1 plus r squared plus so forth, with some unknown coefficients here. Like a1, a2, a3. And if one plugs in such expression instead of phi and solves for this coefficient, something good comes out. But it is a lot of labor. I invite you to follow a trick, which is about 3 times quicker. Okay, now we finally start doing something. So, in case your goal for this meeting is to have a nap, I'll just declare the answer and then you can have it. So, we do want infinite number of solutions. We do want infinite number of energies. But let's start from simplest thing. Finding just the lowest eigenstate and its energy. And it will look as a Gaussian wave packet. So I gave you a warning that we do not say goodbye to Gaussian wave packets when we are done with free electron in free space. It is something universal that will be used again and again. So eigenstate of quantized harmonic oscillator, which can model a lot of chemical systems, will be this Gaussian wave function. So Gaussian functions of elongation from equilibrium. And this one is equilibrium, elongation. And if you draw the wave function or its absolute value square, you see as further away you are from equilibrium, as less the probability to find particles there. Which makes sense. Highest probability at the equilibrium elongation. What else? The width of this distribution for ground state particles. So it is inverse of whatever we see here. So 2 times h bar squared divided by m omega, right? So width parameter. And if you don't care about how we solve it, just analyze the solution. First, if Planck constant is 0, or it is 0 compared to mass and frequency, then the width of this distribution will be 0, which will immediately give us intuitive classical mechanics. So the 2 atoms stay exactly at their equilibrium elongation, right? And then, if we make the mass smaller and smaller, so if you look on smaller particles, proton will be maybe the best oscillating example. And we make the frequency smaller and smaller. Maybe for proton it is loosely bound to some heavy iodine. Then the quantum features will be mostly pronounced. The width will increase. So I just intuitively I guess that for HI acid it will be very, very quantum. Okay, so now you can dim the lights, lean back and fall asleep. We will spend whatever time is left to come to this conclusion. we think that I declare as a shortcut, but it still will be challenging. But doable. So no, I'm pointing on you again. You were the only one who read the small letters. So you have introduced ladder operators to us. Ladder means what? Stairs, going up and down. What will be the stairs? Where will we be going up and down? Along what? Huh? Yes.
Wall.
Huh?
By a wall?
Energy.
Okay.
So if we already, suppose that we already found ground state, first excited, second excited, third excited, and we have their energy. E0, E1, E2, E3. We do not know what those energies are, but suppose that we have it. So we already know that function here will this way, and then I do something indefinite, some functions. They will look much nicer after we solve the questions. So there will be no violation of any codes, no violation of any principles of quantum theory if we will introduce a procedure, a protocol that would convert ground state function into first excited state, first excited state into second excited, third into whatever. So stair-wise, ladder-wise, promote states from one to another. I didn't say any heresy. Was possible. I will just need to prove that it will be useful. And we, at the same time, we can, so it was procedure, one procedure plus. And we can define procedure minus, which will help us to ladder downstairs, to just climb down. And since we know that operators is an abstraction, it is a thing that changes wave function. So we can define new abstraction. We can define such an operator, we can call it, let's say, plus operator, so that if we act with this a plus 1, 2, let's say phi 0, it will generate us phi 1, right? Right now we do not care how this operator looks like, but we introduce an abstraction. You're following. It's not yet boring, but not challenging. Then we can introduce operator minus, or we can skip minus, do just letter A, which will act on, let's say, state 1, and as a result, it will generate state 0. Okay? Why are we doing it? Because we want to find eigenstates, and we hope that these operators will help us to find. Now we are coming to a very intriguing step. So it will be more philosophical than mathematical. If I have, well, table is too high for me for math, but if I have a chair, I can jump on it. If I have 2 chairs, I probably can jump on them from one chair, but I'm staying on the ground. What if I decide to jump and try to go deeper than the ground? Will I succeed?
No.
It will be some injury or like not normal. Convincing. Illustrated. Now, what if we apply this claim down mathematical procedure to the lowest state? Acting by A on psi 0. It will be injury. It will be something not normal. How can we formulate it mathematically? So jumping deeper than ground is not possible. So instead of getting new function, we will get just nothing. Nihil in Latin. Zero. So now we are not students or scientists, we are more, we are philosophers of science. So we today, and you know, in many systems, especially by intuitively, when you pronounce the word vacuum, you may think of vacuum cleaner or vacuum like absence of atoms. But in quantum sense, vacuum is the lowest energy state for any system. Vacuum is ground state. And now the climbing down can be referred to the word annihilation. So what we are doing today, we are annihilating the vacuum. We are philosophers of science and we are annihilating the vacuum. This is the main idea. From now on, we will get some boring mathematical details. So, the statement, the idea, and the possible benefits. So, if there is a big hope that if we formulate, if you find explicit mathematical expression for this annihilation operator, and we will try to practice this annihilation of vacuum, there is a very high chance that differential equation which will come up of this operation will be substantially simpler than Schrödinger equation. It still will be a differential equation, but I went through it and I guarantee it will be so much easier, so much quicker to solve.
So how do you know that you can construct such operators?
No, I do not know. I will just try and see. If I fail, then not good. The steps that we are doing are not typical than mathematicians because they are not so rigorous. So right now you're asking like, how, at least is my understanding how math is working. You're not finding the answer. You're finding whether it is possible to find the answer. Then you prove a theorem. The answer can be found. I'm done. We are a little more practical guys. We need to get something that we can use. Okay. Any additional questions or objections? There are several things in the wish for gifts on Christmas. We want many things, not just to annihilate the vacuum, not just to raise and lower, go on the ladder. There is another item in the list of wishes. We hope that there is a chance to simplify the Hamiltonian because, well, it's possible to memorize this Hamiltonian for harmonic oscillator, but it is already ugly. It has too many symbols, and we confess the principle of least action. We try to do anything we can to write less symbols. and make it simple. So there is another hope that if we develop this creation and annihilation operators, going up and down on value, then it will be a good replacement for Hamiltonian in the following sense. So if we, let's say, stay in state 1 and we apply annihilation, it means we will go downstairs. But if we apply creation, it means we will go back to where we started. So at least we didn't change something, but there is a hope that we can construct this operator in such a way that by doing combination like this, we will get energy. So if you place right factors in front, and if you do math carefully, those creation and annihilation operators will also serve as a replacement of Hamiltonian that will look much nicer and more easier for processing. So that any problem can be done in 20 minutes rather than 3 hours. So we do have a hope. It's not very scientific, but we do have a hope that the Hamiltonian can be expressed as Planck constant times frequency times if you look in textbooks, sometimes it is declared as an answer if you are trying to read things related to physical chemistry, but we will put it as a requirement and we will try to reach it. So like looking upside down. But we know, we already declared that the Hamiltonian is r square, p square, and then some silly coefficients up front. Minus h power squared 2m, right? And omega squared over 2, right? I'm not lying. I'm checking. You please check if I'm not lying. Good. Can you say that it is the same Hamiltonian, or what should we do to make them equal?
One thing equals the other thing.
Yes, but see, here we have product of two operators, and here we have squares of separate operators. How can we? Of course, we can put equality sign and find missing coefficients, but coefficients are already sitting here. How can we wrap up our logic? I was quickly jumping to the next slide, and if you have made a screenshot of it, you may have a guess. So, again, it is not super rigorous, but after we go through the steps, it will be logically consistent. So, do not ask me why it is possible. You will see that it is possible.
Do we need to relate them both back to kinetic energy?
Well, this is kinetic, this is potential. Right? What if we try to represent this creation and annihilation operator as a linear combination of position and momentum operators with some unknown coefficients? I still have a hope, but I will erase the word. Just to have the space. A without dagger and R to P. Linear combination contains both position and momentum, and if we multiply these two things, so we multiply polynomial of two terms, and then the result will have four terms, right? And the result will have a term with p squared times something, a term with r squared times something, and then rp and pr. If you if you select coefficients in a smart way, so that rp and pr will be not there, then we may come to the same Hamiltonian. Make sense? So if we select coefficients in this linear combination in the right way, then this expression visually will be equal to this one. So guess what we have. Now, this is a little strange equation. We already named it for this. Okay. Yes. So I'm trying to complete my Christmas list, what I want from these operators. And with this list, it will be much easier to live after we go through it. So we can also wish that these operators will be conjugate, Hermitian conjugate. So here I put symbol plus, here I put symbol Hermitian. Let me not put any symbol, erase. So here is an operator, here is Hermitian conjugation. And we may wish that upon Hermitian conjugation, we convert the annihilation into creation. And opposite. If you do dagger, Hermitian will be annihilation. What does it give to us if we accept this long wish list? If you go along this way, then in our linear combination, we will get a simplification to mutual relations of these expansion coefficients. We have too many of those. So in each of the terms, we have 1, 2, 3, 4 coefficients. And we need to solve for that, which is, we cannot get one answer with too many variables. We need to constrain our range of search. And if we do require this Hermitian thing, then we can come up with simplifications that the first coefficient in front of position will be the same, and the second coefficient in front of momentum will be the same with minus sign. And under this condition, we are having only two unknown variables. Who told this? That we need to make them equal and find unknown coefficients, right? We are doing this. So our homemade Hamiltonian P R plus P to P times P1 star, and if it is real, it will be the same R. Plus P. And we do want that it will be equal to omega squared 2 R squared, and here H bar plus 1/2. Plus minus. So if we open the brackets, we will see that P1 times P1 star is expected to be equal to M omega squared by 2, right? The P2 times P2 star is expected to be equal to minus H bar squared over 2M. And from here, we can say that P1 is square root of M, square root of omega by 2. From here, we see that if you take square root of minus, it should be imaginary unit. And we still have the cross terms. So for cross terms, the history is a little bit more complicated because we know that they do not commute. So the PR and RP are not equal. And you remember that PR times RP minus RP will be imaginary unit times H bar, right? It's not a surprise. So we can replace one of them by another, but subtract H bar. And this gives us additional equation to solve and make sure that we have this coefficients of linear combination. So we have about 3 minutes until the formal end. Therefore, I am making an excuse for myself for not deriving the last step and declare the answer. But you got the logic, right? Find make a long list of wishes, and then find for under this pressure of this, under constraint of this wishes, find expansion coefficients. And then we are finding two things. First, that because of this complex conjugation, it has imaginary unit with different signs for creation and annihilation. In everything else, they are identical. So coefficient in front of position is square root of mass and frequency, and this 1 over square root of mass. It's one constant. So this is definition of creation and annihilation operators that, as we will see very soon, will match all wishes from our list first, and that will definitely help to find the ground state eigenfunction. I will quickly jump through the solution that will come to this Gaussian shape, but since we may repeat it on Monday quickly once again. So, if we apply this, we annihilate the vacuum, operate A operator to the unknown ground state. It should give 0. So we plug in all the known coefficients, plug in definition of momentum here, and then we are getting the differential equation that has first derivative over position and position as an operator. So no second derivative, no second power. definitely simpler. How do we solve such equations? Well, we take care of coefficients to make them simpler. So this term acts on unknown function, this term acts on unknown function. We can split them on the different part of equation, and then divide everything by unknown function, and multiply everything by incremental position. So then it converts to this shape. Do you have an idea how to solve such equation? You do. So you can integrate this one, which will give which function? Natural log, right? So 1 over function in integral it gives logarithm. And integral of linear function gives power 2, right? And then logarithm? We do not like plot logarithmic functions. We need something more real, and here is logarithm unknown function. So and we need function itself. So why don't we use left and right parts of equation as a power of exponential? So if you do this way, this is what we get on the left, here what we get on the right. On the right we get something reasonable, and on the left, if you take exponential of logarithm, we just get exponential of function, right? And the c becomes n, normalization coefficient that we need to find, and function is equal to Gaussian function. Elongation from equilibrium squared with this trace of fundamental constants and frequency. Meeting is done. Have a nice weekend. Relax as much as you can. No homework for this weekend because you are accumulating strengths for presentations. And see you on Monday.
Hey, Christian, are you going in the lab or the office?
Yeah.
Yeah, okay. I need to do some stuff. Like,
Oh, sure.